Well, let's start then. I just first want to thank you for introducing me, Toby. This is a subject that is very close to my heart and has been for many, many decades. And I'm so glad that we can start this series of webinars. I think the important thing that we want to do today is to explain why reservoir sedimentation management is important. And I think where one can start off is just looking at drought situations. If we look at the United States, droughts, long-term, multiple-year droughts, often occur in the western United States, and that affects every one of us. This is a drought map of 2015 showing intense drought in California. But I think why I say that it affects every one of us is because most of our food comes from California here in the United States. And in order to ensure that we can live through these droughts, what I want to do today is to emphasize the important role of dams in securing our water supply. Now, as you know, there is a big anti-dam lobby nationally and internationally who I think we all may agree are usually pretty uninformed. For example, this book here by James Lawrence Powell is in a big way on Powell Lake Powell. And what he essentially advocates is that we should remove Glen Canyon Dam because the reservoir is almost empty at this stage, not realizing that the reason for that is a multiple-year drought. Similarly, we have international rivers, and on their website you'll find that they say, well, you know, with climate change, it's the wrong time to build dams because they will be empty most of the time. And then we have a former commissioner of the Bureau of Reclamation, Dan Beard, who in his book and in his interviews indicate that he believes that the toilet rebate program will be better than building dams. Now, I think what is obvious is that these populist anti-dam groups do not really understand the issues. This here is a graph prepared by the USGS for 2010 on total water surface water withdrawals in the United States and their uses. And I think what most of these populists think of is just domestic water supply, which is actually pretty small. You know, per day for the United States, it's about 63.9 million gallons a day goes to domestic water supply. But when it comes to producing food, you can see that we have about 100 times more water that we use for producing food, and then for industrial and business applications and thermoelectric power generation, we need about 200 times more water. So I think if we want to talk about sustainably developing our water resources, which is very important for the benefit of this country, I think the first thing that we need to ask is, what do we mean if we talk about sustainable development? And the most succinct and, in my view, the clearest definition has been given in the Brundtland Commission report of 1987, which dealt with our common future, dealt with sustainable development. And it said that sustainable development seeks to meet the needs and aspirations of the present without compromising the ability to meet those of the future. Now, if one carefully look at this definition, what it really does, it emphasizes the importance of intergenerational equity. And what that means is that we are requiring fairness between generations. Surely, environmental stabilization is important, but from a sustainable development point of view, environmental stabilization is a desirable consequence of sustainable development and is not the objective of sustainable development. And I think this is very important because there's a general use of the word sustainability, which means different things to different interest groups. But what we are really interested in is sustainable development. So if we want to summarize that, what sustainable development is to harmonize environmental, engineering, and economic aspects of projects with the prime objective to create intergenerational equity. That is emphasizing life quality to ensure that for not only our own generation, but for generations to come. So having defined what we mean by sustainable development, I think the next question to ask is, how do we sustainably develop a resource? There is an economist who worked for the World Bank in the 1980s by the name of Herman Daly, and he was very deeply involved in developing the World Bank's sustainable development policy. And he came up with three things to say, how can we sustainably develop resources? And he distinguished between renewable and exhaustible resources. And he stated that renewable resources, if we want to use those sustainably, we should use them at a rate that is smaller than the rate of regeneration. And in the case of exhaustible resources, we should use them at a rate that is smaller than the rate of development of renewable substitutes, which is very difficult. And the third thing is that pollution does not exceed the rate by which the environment can assimilate it. So in essence, if we look at renewable resources like wheat, as long as our rate of consumption is less than the rate of regeneration, we can sustainably develop a resource like that, the renewable resource. But if we look at mining, which is really an exhaustible resource, it's really no way to say that we can sustainably develop mines or similar products. So I guess if we start looking at water, the question to ask is whether water is a renewable or an exhaustible resource. And to get some idea of how much water there is on Earth, we can take the diameter of the Earth as a reference, which is 7,972 miles, and then compare that. If we take all the water on Earth, all the water in the oceans, in the polar caps, in groundwater aquifers, and we put that in a sphere, it will fill a sphere with a diameter of 864 miles. That's all the water on Earth. And because there's only so much water on Earth, there is obviously an exhaustible resource. But what we are interested in is fresh water. So if we now take all the accessible fresh groundwater on Earth, and we put that in a sphere, it'll fill a sphere with a diameter of 42 miles. And if we take the other resource, that is rivers, and we take all the water in the rivers on Earth, and put that in a sphere, it'll fill a sphere with a diameter of 10 miles. That is smaller than the distance that most of us commute daily to work. However, I think the good news is that we can view that as a renewable resource because of the hydrological cycle. So now the next question is, of these two principal freshwater resources, that is groundwater and rivers, Which one of those two have the greatest potential for sustainable development? So to answer that question, what we can do is to go back to Herman Daly's definition of how do we sustainably develop a renewable resource and compare the rate of usage of water to the rate of replenishment of these two resources. And a good proxy to use to get some idea of the rate of replenishment is to use the residence time of these resources as a proxy. So the residence time is the time it takes for a drop of water to enter at the most upstream end of the resource and move through it completely. And if we look at all the fresh groundwater on Earth, the residence time for that water is 1,400 years. And for rivers, the residence time is 16 to 18 days. So if we look at this from a different point of view, say, for example, we had the ability to instantaneously remove all groundwater on Earth in an instant. It'll take 1,400 years for it to reestablish to the state it is in now. And on the other hand, if we remove all the river water on Earth in an instant, it'll take about 2 weeks to replenish. So if we compare that now to the daily use of water, we can conclude that the replenishment rate of groundwater is much longer than the usage rate of water. Okay. So just from a visceral point of view, we can conclude that river water or rivers most probably has a much greater potential for sustainable development than what groundwater has. And if we look at research confirms that. This here is a map of the major aquifers in the world, and the ones in gold are the ones that are in peril. And there's a concept known as the groundwater footprint that was developed by University of Utrecht in Holland and the McGill University in Canada. They worked jointly on a project. And the footprint is the area that you need to replenish an aquifer as it is used. For example, if you look at the bottom of the screen at the North Arabian aquifer, it has a groundwater footprint of 48. What that means is that the area you need to replenish that aquifer through rainfall is 48 times the area of the aquifer itself. Or viewed differently, the amount of water that is annually extracted from this aquifer is about 48 times of what is replenished. And if we look at the United States, there's a High Plains aquifer that is known as the Ogallala aquifer in the general area where I live. It stretches from Texas to Nebraska and is a major agricultural area. And that footprint is 9, which means that we are extracting 9 times more water out of that aquifer than what's replenished. There's also the aquifer of western Mexico there, where we get a lot of our food from, with a footprint of 27. And what is not shown on there is the Central Valley aquifer of California, and that has a footprint of 7. So purely from a food production point of view, we are here on the wrong path. So I think what we can confirm is that river water has a much greater potential for sustainable development than groundwater. But the issue with rivers, as you know, is that the flow in the rivers vary with time. And this hydrologic variability requires storage to allow us to reliably supply water in periods of drought or low flow. And there are essentially 2 time scales we need to look at. One is the within here time scale, and the other one is a multiple year time scale. So if we look at within here, this is a hydrograph with flow on the ordinate, and the time is expressed in months, and this is 36 months, so it's 3 years. So what you'll notice for this particular hydrograph is that the annual hydrographs roughly look the same, and there's one season, a dry season every year, where the flow is lower than normal, and we may need some small amounts of water storage to supply water during those seasonal low flows. But then, in many parts of the world, we may experience multiple year droughts. And this hydrograph, each bar in this hydrograph gives you the volume of water that flows in that river during a particular year. And the red line is the mean annual flow over the long term. So for example, you'll notice here, there is a period of 11 years where the annual flows in the river are lower than the mean annual flow. So if we want to use a river like this to supply water, we need very large storage to be able to carry us over that dry period. So let's just distinguish in a sort of more graphical way what this means. We can prepare a graph on the ordinate as healed as a percentage of the mean annual flow. That means the amount of water we can supply out of that river as a percentage of the mean annual flow. And at the bottom, we have reliability. So in cases where we have very low hydrologic variability, like in the northeastern United States, you can see with no storage or just very small seasonal storage, that we can supply about 80% of the mean annual flow of that river at the 90% reliability. However, if we want to go to areas with high variability, and we look at that, and we don't have any storage, because of these multiple year droughts, we cannot guarantee any water at the 90% reliability. So what can we do? If we add storage to this kind of river, and say the storage is equal to 1 times the mean annual flow in the river, then we can change the situation. And what now happens is that at 90% reliability, we can guarantee about 70% of the mean annual flow in this river. So storage is quite an important feature. What this map shows you are areas in the world where these multiple year droughts occur on a regular basis. And you see here that the Western United States is one of those candidates. But if we want to look forward, what we also need to say as well, if climate change proceeds, how is that going to impact our water supply situation? And there are 2 important variables. The one is changes in the mean annual river flow, and the other one is how climate change will affect the hydrologic variability of river flow. Now, there's been many studies that studied how mean annual flow will increase or decrease over the years, and the yellow and red colors here are areas where river flow will decrease. And you see the Western United States is a candidate for decreasing mean annual flows. So is most of Europe around the Mediterranean and other places. But even more important than this is how hydrologic variability is going to impact the reliability of water supply. And generally, climate scientists agree that with climate change, hydrologic variability is going to increase. And this here are some simulations by NASA on how soil moisture will change over time. And what you'll see is that as time goes by, droughts will be longer and more severe in most of the USA. So this is something we need to deal with. So how do we deal with it? What I have here is a graph. Again, the ordinate gives you the percentage of yield. Yield is a percentage of the mean annual flow. And in the abscissa, I have hydrologic variability. That is representing climate change. So as hydrologic variability increases, so does the effects of climate change. So what we can do now is to draw a curve on this to determine for 99% reliability how climate change may affect our effectiveness to provide water. And this curve here is for a storage volume that's about 60% of the mean annual flow. Now, most of the places in the world have a hydrologic variability of about 0.3 to 0.4. So if we say that climate change will increase hydrologic variability from 0.3 to 0.6, you can see that there will be about a 30% reduction in the amount of water we can supply at 90% reliability. Now, if we increase the volume of the reservoir we build, that changes, and now we have about a 15% reduction in the amount of water we can supply at 90% reliability. And if we increase the reservoir volume even further, that reduces to about 8% reduction. So just that as general conclusion is that an important way to counter the effects of climate change is to have reservoir storage that is as large as possible. So having said that, let's look at what happens in the United States. This graph here on the abscissa is years, and then on the left ordinate, you have cumulative volume. That is the cumulative reservoir volume that's been built over the years in the United States. And this is for large dams. And I got this information from ICOLD, and it's for dams with known construction dates. And you'll see around about 1980, there is a very little addition to reservoir storage. Then on the right ordinate is population, and you can see that before the 80s, there was a greater rate of adding storage volume than the population rate, and after that, the population rate continues to grow, but the amount of the volumes that we're adding is not keeping up. But this is not the total story, because reservoir sedimentation plays a big role in determining how much storage space we have available. And if we look at the United States, there was some research done at Colorado State University by Graf et al. And they divided the country into regions showing annual storage loss as a percentage. And you notice that big parts of the western United States, that the annual storage loss due to sedimentation is greater than 2% per year. California is about 0.8 to 1.2%, and you can see the other areas there. So let's just assume that we have a 1% storage loss per year throughout the United States as a general average. What you see on this graph is two curves. You have cumulative volume on the ordinate, and here is on the abscissa. And the upper curve is the cumulative volume that we added by construction of dams. And then for the 1% sedimentation rate, we have a lower curve. You can see roughly about 1980, that is where we are losing more storage space than what we're adding on an annual basis. If we go one step further and we say, okay, let's look per person in the United States what's happened. This year is for an assumed 1% sedimentation rate. And you see around about 1972, 1973, that we have a turning point. So what is happening now is the storage per person is on a continual decline. Now, what can you do about it? Well, there are various reservoir sedimentation management techniques that one can use. And you can classify them in various ways. This is one way, as to have three categories. One is to manage the amount of sediment generated in a catchment. In other words, we're trying to reduce the amount of sediment going into reservoirs. The middle one here is to route sediment. In other words, what we're trying to do in cases like that is to keep the sediment transport capacity in the reservoir as high as possible so that we can minimize the amount of sediment that deposits in the reservoir as the flood goes through it. And the third group is a sediment removal group. In other words, what we're trying to do there is to remove sediment that is already accumulated in reservoirs to increase the storage space. Now, I'm not going to go through all these methods. That is something that Gregory Morris will deal with in a following lecture. But the message is that there are things that we can do. Now, the question is, why haven't we done this in the past? And I think one thing that we didn't realize is that reservoirs have a dual nature. In other words, they can be either renewable or exhaustible. And this is a deliberate choice that we make. For example, if we have, if we build a dam across a valley, the valley upstream it is a storage space that we create. And if we decide as designers and operators to allow this storage space to fill with sediment, then we make the choice to classify it as an exhaustible resource. The alternative, if we design the dam and the reservoir in a manner that we can remove the sediment, in some cases in the world there are examples where you could remove everything, in other cases not everything, but we can get to a stable condition. If we apply these methods, then we can, by choice, classify this resource as renewable. So this is something that we do. We do it in our designs, the choices we make, and the way we operate it. Now, one important thing that affects those decisions is how we conduct economic analysis. This here is just a simple timeline. In the bottom are the costs. The first here is 0. We have the cost of constructing a dam. And then at the bottom, those blue dots are the maintenance costs throughout time. And then on top of the line are the benefits that we get out of the system. Now, how these, and I'm sure all of you in the audience know this, how we evaluate this is to calculate what's called a net present value. So what we generally say is that we believe that things that may accrue in the future are less valuable to us than what they are right now. And one thing that we'll notice is there's never allowance for the cost of storage loss. We don't allow for the cost of removing a facility at the end of the timeline or to build a new dam to supply water. So why don't we do that? Well, the thing is that interest rates that has been used in the past, and I must say the World Bank has changed it now, they have a lower rate, but if you use an interest rate of about 10 to 12%, anything that happens after 30 or 40 years is inconsequential when it comes to calculating the net present value. For example, in this case, say we add a cost D to replace the dam or to remove a facility after it's silted up. If we discount it and it's more than 30 years out, its value is insignificant and we can just ignore it. And that is the standard approach. However, there was an economist by the name of Hotelling, and he authored a paper in 1931 called The Economics of Exhaustible Resources. And that paper never really got any attention until recently, when we became more interested in sustainable development. But what he said is that the price of a resource, an exhaustible resource, increases with the discount rate. So if we have the price of the resource increase with the discount rate and we discount it, it means that its value doesn't change. So for example, in such a case, if we would have the cost of replacing the facility in year N and we apply the Hotelling principle, it means right up front that that present value remains exactly the same at D. So this changes the whole way that we can analyze the economic value of reservoir sedimentation management. I must just say this is the sort of extreme example. What is done to facilitate or to recognize future importance of future conditions these days is that the people, economists may use a declining discount rate. For example, the United Kingdom and in France, that is standard practice for long-lived infrastructure. The other thing that we need to look at is our design philosophy in civil engineering. Conventionally, we use a design life approach, and that consists of planning and design, construction, operation and maintenance, and then we say we dispose of it. Now, for conventional infrastructure, not dams, but say, for example, roads, that is a completely logical way to deal with the problem. Because we may design a road, say, for a design life of 15 years, but at the end of 15 years, we refurbish it, and we can use it in a sustainable manner forever. But if it comes to dams, once the dam is filled with sediment, it is virtually impossible to recover it. So what we've been promoting since about 2003 as part of a World Bank effort is this concept of a life cycle management approach. And the whole idea is to plan and design infrastructure, particularly dams, in a way that we can use it in perpetuity. Now, I know that that sounds like a lofty goal, but it consists of constructing the dam, doing operation maintenance, removing sediment on a regular basis, refurbishing it, and using it forever. There are examples of this. For example, Three Gorges Dam, that is got a lot of flack for many other things, but that facility is designed with the intent to use it in perpetuity. There's a sediment management approach in there, and that is what they're doing. Now, how do we implement this? One way is to start with planning for both existing and future reservoirs. And this is a project that I participated in with Fichtner and with Gregory Morris and myself. And we've developed a concept known as the RESCON approach that was originally published in 2003 when I worked with Alessandro Palmieri and others. And we've now updated that. And it is it's got a software package with it, which focuses on trying to create intergenerational equity. implement a life cycle management approach by recognizing the dual nature of reservoirs. It provides you with a means of determining the technical feasibility of sediment management for a particular site. There is an economic optimization in it, and you have a selection between using a constant discount rate of 0, creating a sinking fund to deal with future issues, or to use a declining discount rate. It also has a component where you can look at the impact of climate change on sediment management and whether you're making the right decision if you look at all the deep uncertainties introduced by climate change. And it also deals with environmental and social safeguards. I'm just introducing you to this. Essentially what it is you have some user input, and it's very minimal input because we were focusing mainly on the pre-feasibility stage of projects. And then what it does is you look at all these different sediment management techniques. The software does an analysis for you, a sedimentation analysis, to get an idea whether any one of these techniques are not technically feasible, and which ones are technically feasible. It does the economic analysis, and in it comes out with what kind of solutions may be possible. Some of them may be non-sustainable. And then you have the option of decommissioning it, or if you have a hydroelectric facility, to turn that just purely into a run-of-river facility. Or there may be a sustainable solution. What it uses a lot is previous experience. There is experience in managing sediment and reservoirs. And this is a graph that shows you give you some idea of what may or may not work in certain situations. The ordinate, it gives you the volume of the reservoir divided by the mean annual supply of sediment. So the units that come out of it is years. So that 100, for example, it tells you roughly that, well, the lifetime of this reservoir may be 100 years. And then at the bottom, you have the capacity of the reservoir divided by the mean annual flow, which gives you an idea of the relative size, the hydrological size of the reservoir. And then plotted on there, there's a number of projects where sedimentation management was either successful or not. And there's a dividing line, that black thick line, which gives you an idea. If you're below the line, most probably your project will be non-sustainable. And above the line, you have the potential to be sustainable if you implement reservoir sedimentation management techniques. And then if you look at these blocks, it gives you an idea of what kind of sediment management technique you may use and may find to be technically feasible. At the bottom of this slide, I also have a URL for the International Hydropower Association, and we're also working with them to have this particular page. It's not generally available on their page yet, so if you use that, you'll get to the site. And the whole idea is there that we'll have projects throughout the world where sediment management has been implemented and has either been successful or not. So you can use those to see how it fits in with your project and what might or might not be done. So the general approach with this RESCON is that you're working at a planning level, a policy level, pre-feasibility level. You use the RESCON approach to determine the technical feasibility of your project, economic value of it, how climate change may affect it, and you can also look at environmental and social features. Once you have that knowledge, you can move on then to a feasibility study, which is more detailed, and eventually to final design. So what are the key messages that I try to get to you today? The first thing is, I think we should never use just the word sustainability. We should talk about sustainable development, because that's really what we're doing. And the most important thing of sustainable development is to create intergenerational equity. And to recognize that as important as environmental conservation is that is a desirable consequence of creating intergenerational equity. And sustainability is that the objective of sustainable development is not to conserve the environment, it's to create intergenerational equity projects that enhance life quality. Next message is that the preferred water source that has the greatest potential for sustainable development is rivers. Groundwater is less desirable. Thirdly, we have climate change impacts. And one of the biggest impacts of climate change is increases in hydrologic variability. And to deal with that, we need more and more storage space. And there's deep uncertainty that's introduced that we can deal with in, for example, the RESCON approach. Next is if we look at net storage space in the US, and I must also say, this is not only in the US, this is internationally, is that currently we're losing more storage than what we're adding. So we are not preparing for the effects of climate change. And then we need to preserve storage space. You know, in existing reservoirs, they are filling up rapidly with silt. And we need to figure out ways to increase the storage space in those reservoirs. And for future reservoirs, we need to carefully look how we design and operate them. And we need to move away from the design life approach when it comes to dam design and adopt a life cycle management approach. And then when it comes to the feasibility of sustainable development, it's very important to understand that reservoir storage has a dual nature. It can either be exhaustible or renewable, and that we determine what that classification is, as designers, as operators. It's a deliberate choice that we make. And we definitely have to look at the way that we conduct the economic analysis of these projects. And what I've introduced you to, I've just given you notice of it, is that there's the RESCON 2 approach now that provides you with an easy means at pre-feasibility and policy level to look at the technical feasibility of implementing various reservoir sedimentation management techniques in your project. It provides you with a facility to determine the economic optimality of various solutions you may look at, and it also allows you with the ability to look at climate change impacts. So in conclusion, what I want to say is that we need to provide leadership. I think the fact that the anti-dam lobby has done and achieved what they have achieved in the 80s is partly due to our inability to give leadership and provide understanding of what is important. We have to create intergenerational equity by balancing the engineering, economic, and environmental aspects of projects. It's important to consider the effects of climate change and understand that we're going to need more storage in the future to reliably supply water. And we need to be the voice of reason. I have a photograph here of John Briscoe. And as many of you may know, I'm a South African. I'm very proud of him. He was a South African. He worked with the World Bank for many years. And when the International Commission on Dams promoted to not build any dams or was a negative force against it, he was a very strong advocate in the World Bank for many years to promote and create understanding of how important dams are. And I think we need to follow his example. I have, in the end of the presentation, I have some references. This is a book that I authored, Quenching the Thirst, which gives, it focuses mainly on sustainable water supply and climate change, and essentially goes into deeper discussion of the concepts I presented to you. And then there are these two other more recent publications. The one on the left is called Extending the Life of Reservoirs. And it's a book that Gregory Morris, myself, and Pravin Karki from the World Bank authored. It's intended for a technically or scientifically informed audience or readership. It goes into a lot of detail and gives a lot of experience on reservoir sedimentation management, what worked and what didn't work. And on the right-hand side, you have the manual for the RESCON2 software that is complementary to this book. So with that, Toby, I would like to conclude.
Excellent. Thank you, George. Great presentation. So we've had a number of questions that come in. I noticed that we have a few minutes left until the end of the scheduled end of the talk, I should say. So how about we go ahead and start with some of the questions that we've gotten so far. If people have additional questions, feel free to, you can send them privately to either myself or Tim Randall, or you can send them to everyone if you don't mind other people seeing them. So George, the first question for you is, can maintenance of our existing reservoirs eliminate or reduce the need to build more reservoirs?
Well, I think the thing is, I think that there's a twofold answer. We need to maintain our existing reservoirs to try and keep up. But even if you take that curve of the original storage that we created and you calculate the per capita storage, we start to have a negative trend in 1980. It's only 8 years after the one with the 1% assumption of sedimentation. So the answer is that we need to maintain our existing reservoirs, firstly, and secondly, we need to build more dams. We will not be able to survive at the level of economic activity and life quality we have at the moment if we do not do that.
Okay, thanks. Okay, the second question is, what about the cost calculations associated with reduced or lost flood protection as sedimentation proceeds?
You know, that is something that is an important feature. I had a student from Tsinghua University that worked with me a couple of years ago here in Denver. He was a PhD student. And we've published a paper in the Journal of Water Resources Planning, ASCE, dealing with this problem, amongst other things. We took three gorges as an example. And obviously, the flood control portion of it is an important portion. If you're losing storage and you cannot control your floods, that is a cost aspect that needs to be considered. If you need a reference to that, I can give that to Toby, and you can supply that to the audience.
Okay, thanks. Okay, looks like we have time for a couple more. Another question is, do we have a sense of how much sediment volume has accumulated in U.S. reservoirs and what the cost to remove it might be? One note that we added here is that it might be cost prohibitive. Some estimates say thousands of dollars per acre foot by conventional dredging.
Yeah, well, the thing is, dredging is one of the techniques. We have other techniques to do that. The thing is, it may be cost prohibitive. And that is why one needs to look at the project by project basis to see what is the best way to deal with it. The common approach is usually to just think of dredging, and that is not cheap. But you know, the most effective way generally to remove sediment is through drawdown flushing. It has its ups and downs on the downstream side. If you have too high sediment concentrations, obviously that is going to be negative from an environmental point of view, but it is implemented. It is implemented on a regular basis, actually in France, for example, in the Loire River. It is not something that that cannot be done. So I think the question is that, or the issue is, I think a investigation, I would think, was probably at least a statistical investigation nationally needs to start to see what is possible and what is not possible. It's not a question one can just answer in the general, but it is on a case-by-case basis.
Okay, thank you. Okay, we have had a few different questions along this lines. I think generally we'll say, here's the question. What is the capacity to build or enlarge more dams and increase reservoir storage capacity? And presumably, I think that would be, at the rate of reservoir sedimentation.
So I didn't quite understand the question. Just ask the question again.
Yeah, what is the capacity to build or enlarge more dams and increase reservoir storage capacity? So in other words, are there additional dam sites, or can we raise our existing dams to increase capacity?
Well, that is the big problem. I mean, most of the good dam sites have already been used. So that in itself is a problem. Increasing the height of dams increases reservoir storage, but that is not a permanent solution. If we want to create intergenerational equity, we can perhaps raise dams in the short term, but we have to figure out how to deal with the constant reduction in storage volume in the long term. And that's not the final solution. Yeah, that is a good question. If you look nationally, I think there's very few really good sites that can still be used.
Okay, thanks. Yeah, I think we'll end on this last question here, and I'm going to paraphrase here. Isn't it true that some of our aging reservoirs no longer make sense to maintain, and that it might make sense to remove some of those?
Yeah.
And I think part of that question is, it seems like demand management should be part of our water resources planning.
I would agree with that. The thing is, a graph that I didn't put into this presentation is if you look at the usage of water in the United States, since about 1975, it tailed off in spite of increase in population. So we're already conserving water. I'm not sure how much more we can conserve. I agree that is a lofty goal, but that has already happened. What is the second part of the question? Can you just?
I think it's partly a comment that demand management should be part of the water resources planning.
I agree with that, but I think there are limits on how much one can manage that. Like I say, for instance, 1975, the total amount of water volume that we used has virtually become constant, although the population increased. If you look internationally, that whole concept of demand management is just not even on the table, because most of the people in the world, and the vast majority of the people in the world, doesn't even have the minimum amount of water that they need for a reasonable life quality. But the United States, one can try and do that, but I think personally, that doesn't solve the problem. And that is what Dan Beer tried to say with his toilet rebate program. But the biggest amount of water is used in agriculture and in industry in the United States. Internationally, most of the water is used by agriculture.
All right, thanks. Okay, so I think we're going to have to stop there. There's some other good questions that have come in, but why don't we hold those actually for the next talk, for Greg's talk coming up next month. They're a little bit more specific to some of the technical aspects of sediment removal. So George, I just want to say thanks very much. Appreciate your talk. That's a great talk. And I would like to just advertise that the next talk is by Greg Morris, which will be next month, February 22nd. And we will be sending out an email to everyone about it. The title of his talk at the moment is Reservoir Sedimentation Management Options and Data Needs. So thanks everyone, and look forward to seeing you next month. We did make a recording of the presentation today, and we will try to get that up on the web in a week or two. All right, thanks very much. Take care.
Thank you. Bye.